Welcome to a lesson with Dr. Powell. Let's suppose that we want to expand something, multiply it out, where we have a power that's kind of high for building Pascal's triangle. The numbers get pretty big down here. Well, we can still do a few things, even if we don't build Pascal's triangle. For instance, let's suppose we're looking for a term that has x cubed in it. What would y be? Well, y to the 10th, right? Because these exponents have to add up to 13. So we know kind of our like terms are going to be something like this, where we have x to a power, y to a power, where the power exponents add up to 13. Then the question comes, what is this coefficient? Can we do this individually instead of building out the whole triangle? And we actually can, if we remember what this means. This coefficient is actually the number of like terms that look like this that we're adding up. If we expand and multiply this all out, after all the distributing, we have lots of these. And this coefficient is how many like terms we have of that kind. Now, this number is precisely, well, let's think about it. If we had 13 of these guys, we won't do 13. Okay, so we have 13, however many they have, dot, 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 here, from here to here. This number is the number of ways that we select 3 of these factors. So any 3 of them, to be the factors that we pull an x from. Remember how we discussed that when you multiply this out, we're going to get lots of like terms, and every term has something coming from each one of these factors, just one thing from each one. Now, if 3 of the factors have an x being pulled from them, and the rest have a y being pulled from them, then that would contribute to this coefficient, because we get a term that looks like this here. And so we're basically looking for the number of ways of choosing 3 of the factors from the 13 factors of x plus y to have x pulled from them. See that? We have a notation for that. We have 13 things. How many ways are there of choosing 3 things out of the 13? So that's equal to the number of ways of choosing 3 things, 3 things from 13 things. There's actually a way to compute this idea. 13 choose 3. It looks kind of like a matrix notation a little bit with this guy and that guy, but it has a specific meaning for us, at least in this context. So this is contextual, what the symbol means. This is called a binomial coefficient, coefficient right here, which is proper and fitting since x plus y itself is a binomial, 2 terms added together. And in the expansion, these coefficients, they're often called binomial coefficients. This is the notation of the coefficient that you would put right here. We still haven't figured out how to compute it, but at least we have a notation for it. The coefficient that fits right here. So there's going to be a lot of things plus, this sum really is a lot of things added together, and we're only looking for one particular part of the sum. But using this, but at least we have something to start with. We have a notation for what we're after. We're after that coefficient, and we'll just notate it as 13, but we'll read this as 13 choose 3. That's 13 choose 3. How can we compute what this number is? Okay, 13 choose 3. How can we compute it? Well, we start with the following idea. Imagine that you have 3 different boxes. And we think, all right, how many different ways are there of choosing one of the factors, like first factor, second, third, fourth, whatever, um, to be in this box out of the three things that we're choosing? Well, there's 13 different choices for what to put in here. Now, since I've already chosen one, how many are left to go into here? Well, there's 12 different options left over. So there's 12 different ways that I could select one of them to go in that box. Then what about what about this box right here? Since I've already chosen 2, there's only 11 left, and I can choose any one of those 11 to go in here. All right. Now this is too many different choices, but the reason why it's too many is because the first guy I chose here in this setting could have actually been the last guy, and maybe the last guy could have been the first guy, and that would have been counted in here, double counted in this particular counting. So basically what I need to do is I need to divide by the number of ways of rearranging 3 things. And then I got the precisely number of ways of choosing 3 things from 13. So we divide by the number of ways of arranging 3 things. And actually the way of arranging 3 things can be thought of in a similar process. Out of the 3 things, the thing that would go here, there's 3 choices, then there's 2 choices and 1. So that's what we divide by. But it kind of has a nice feel for it. Notice 3, choose 3 things. Notice 3 boxes on the top, 3 boxes on the bottom. It's a fraction. And on the top, we start at the top. On the bottom, we start at the bottom. Start at 13 and go down consecutively. 12, 13, 12, 11. The bottom, we start at 1, we go up. 1, 2, 3. So now we can make this computation. So 6 and 12 reduces that reduces to 2. 11 times 13 is 143, and multiply that by 2. So that would end up being 286. So the coefficient that we were after is 286. 286x cubed y to the 10th. So that's the coefficient right there. Now, it might be interesting to note that the number of ways of choosing 3 of the factors to have x from it is the same way, should be the same number of ways for choosing 10 of the factors to have a y pulling from them, which actually builds a symmetry. 13 choose 3 should be the same as 13 choose 10. But we saw the symmetry in Pascal's triangle. Notice how every line was very symmetric. Like these guys were the same. Across the middle, they're the same. If 3 plus 10 equals 13, then this number is the same as this one. So if we ever have to compute something like this, let's do this one, because there are less numbers in the numerator and denominator. And so that's something else to think about. This also brings up another point, that if we have x to the 10th and y cubed, what would be this coefficient? It would also be 286, because we're computing the number of ways of choosing 3 y's from 13, which is the same as this number, 13 choose 3. So we actually just discovered 2 coefficients in the expansion. And we could likewise go through each one. And if the number is fairly large, this method may be more efficient in building out Pascal's triangle. Thanks for watching.